Good morning, ladies and gentlemen. Thank you for staying for my talk. Achieving both economic and environmental objectives for a solar farm with co-located battery storage. So firstly, motivations. We know that in a future world with lots of wind and solar power, we're going to need energy storage. Now, flexibility is great, but it's not going to get us to 100% renewable. Now, a lot of existing work has been done on grid-connected batteries, providing ancillary services, and this work has tended to try and maximize profit while taking it for granted that just by providing this service, they're doing something green. They're allowing more renewables to connect to the grid, but just allowing it is not the same as guaranteeing it. And furthermore, we know there's an environmental cost to manufacturing and recycling batteries. So what we aim to do in this project was to explore and quantify this relationship between the environmental and economic imperatives. To do this, we developed a model in MATLAB, whose context I will describe next. I'll then explain some details of the simulation. I'll show some results and discuss the implications, and that will be the structure of the talk. Okay, so the situation being modelled is inspired by the Lymington Array in the UK. It's owned by a cooperative who collects a fixed fee per kilowatt hour from an energy retailer from this solar farm feeding power directly into the 11 kilovolt distribution network. And it's not unique at all amongst solar farms of this size in that there are constraints on the local network that mean the Lymington Array cannot export more than 2 megawatts. So at the design stage, the PV generation capacity was oversized by 20% according to standard practice, because this gives a boost to generation which more than compensates for the small curtailment losses at summer noontime, which you can see in red at the top graph. So supposing there were enough land and funds to expand the generation capacity, would it be possible to install some battery storage to absorb the energy that would otherwise be curtailed due to these network constraints, and then sell that recovered energy to try and recoup the costs of the battery? Well, to simulate this, this is the setup. There are in fact multiple strings of PV in parallel, all connected to a 3-phase AC grid, but we approximate them as a single unit for simplicity. And similarly for the batteries, we approximate them as single battery connected via a single power converter. And so the operating regime, there are 2 regimes. During the day, all PV generated is exported up to the 2 megawatt limit, and then any excess is used to charge up the battery up to a power limit, which we set in the power converter, and no charge is allowed above 90% state of charge. And you can see on day 165, both the power limit and the energy limit kick in soon after each other around midday. And so you can see the curtailment in red there. Now, during the night, all the energy that has been stored in the battery at 6 p.m. is then slowly discharged over 14 hours. And you can see the very small amount of discharge in purple on this graph. So all the battery discharge plus any residual PV generation is exported to the grid at night, and the discharge is stopped at 10% state of charge. And these limits are there because for standard practice to preserve battery life. Okay, so in this study, we looked at the effect of some different PV expansion plans up to 3, 3.5, and 4 megawatts. For each of them, we varied the battery capacity and the power converter capacity, in other words, the battery energy and power. And we looked at the effect of different battery prices from £400 per kilowatt hour down to £50 per kilowatt hour. And these currency conversions were correct as of mid-August. So for each case, we calculated the net present value, that is the discounted profit over a 25-year lifetime, and an analogous concept for CO2. So to calculate that, we take into account the costs and the embodied carbon of each of the components, PV, battery, and converter, and the sale price of electricity and the carbon intensity of generation on the rest of the grid. Right, so results. You can see on the left, when we vary the battery energy and power independently of each other to try and find the combination that maximizes lifetime CO2 savings. And so for each PV expansion plan, we find, unsurprisingly, the more you expand the PV, the larger and more powerful the battery you need. And we're able to save quite substantial amounts of CO2, several kilotons, compared to the base case of 2.4 megawatts and no battery, which saves around 14 kilotons. Unfortunately, there is a loss incurred in each expansion compared to the base case, and this loss runs into millions of pounds. Now, that's for a battery price of £400 per kilowatt hour. If we reduce that, there's an improvement. Now, instead of millions of pounds of losses, it's down to hundreds of thousands of pounds. But the thing is, we're saving carbon, but making a loss. So this is indicating a misalignment of incentives here. So what happens if we try to realign them? This is what we did in calculating the carbon price, which we define as the net loss for the system compared to the base case divided by the net lifetime CO2 savings, again for the system compared to the base case. And this carbon price could take the form of an international tax on fossil fuels, which would then raise the electricity sale price, or it could be given as a direct subsidy to the solar and battery plant. At this stage, it doesn't matter too much. All that matters is it's enormous. It's up to £547 per tonne, and you compare that to what the World Bank recommends as a carbon price to try and keep global warming below 2 degrees Celsius, £30 to £60 per tonne. Now, another way of thinking about this carbon price is as a metric to help governments decide where to invest in climate mitigation strategies. So you can see, before even considering subsidizing a PV and battery plant, it would be better to encourage more wind and solar power elsewhere, where the grid is less constrained. And for comparison, I include Hinkley C nuclear power station, which is still in the process of construction in the UK, and it's proposed to give a strike price subsidy of £92 per megawatt hour, which with prevailing market conditions I estimate as roughly £100 per tonne is the value that the government is assigning to this service that Hinkley C provides in climate mitigation. Now, if battery prices come down to the lowest that we studied here, then it starts being comparable. And we've got to remember as well, when the feed-in tariff was introduced in 2010, there was an enormous subsidy given, especially to solar power, which would have equated to about £700 per tonne as a carbon price. Now, some may criticise that and say, oh, it was a waste of money, the government should have spent that on more cost-effective climate mitigation. But on the other hand, if there wasn't this scale of intervention from the governments of the UK, Germany, China, elsewhere in the world, could the price of solar power have dropped quite as far as it has done now? We don't know. So you could say, in fact, it's not just carbon that's being priced here. It's also stimulating an industry, creating jobs, and then it becomes quite hard to talk about this kind of cost and value. Now, I'm not advocating enormous subsidies for PV and battery plants. I'm just making the point that crazier things have happened in the past. So one last result, a sensitivity analysis. We varied the price and embodied CO2 for the different components, and here we see the minimum and maximum resulting carbon price. There's enormous variation, but it doesn't really change the conclusion that if you use a battery solely for curtailment avoidance, then it's not really worthwhile without significant intervention. So, given that, what can we do about it? Well, cheaper batteries would help for a start, but as we saw, a huge carbon price is still required, even for a battery price as low as £50 per kilowatt hour. Similarly, second life electric vehicle batteries could be a good source of cheap batteries, but really it depends what's going to happen to the market, and there's a limit to how low that price can go. Now, longer lasting batteries, of course, will reduce the replacement costs, again, which will help the economics. But then second life batteries are unlikely to last as long as new ones. Really, their value would lie in the environmental benefit of diverting these electric vehicle batteries from disposal or recycling when there's still some value left in them. Now, to really achieve financial sustainability, we need to start looking at other revenue streams. For example, negotiating a higher electricity sale price with a load center, supplying them via a private wire. And then really lucratively, we would need to look into providing ancillary services such as frequency regulation. And the challenge then is to balance the requirements for this with the requirements for curtailment avoidance, because that is where the CO2 savings really come in. So this is the plan going forward, to try and optimize these two objectives, net present value, representing the financial, and CO2, the environmental objectives. Though, of course, we mustn't forget other greenhouse gases and other pollutants as well. We can't focus solely on CO2. So in the design process, we'll have to look at component sizes, of course, the service utilization, how it's accounted for economically, and also the degradation of all the components and all these various factors from the system operation that affect the degradation, which then affects the replacement schedule and therefore the replacement costs. So it's all very convoluted, but should be an interesting project for the next 2 years. All right, well, I'd like to thank my sponsors. Thank you to the conference organisers for the opportunity to speak here today. There's still quite a lot of time left, so I'll invite questions at this stage.